In this video, we'll use disks to find the volume of a sphere. This is the 6.2 pre-class video. Alright, in this video we're going to find the volume of a sphere. We already have that formula, 4/3 pi r cubed, to find the volume of a sphere, but the method that we develop in this video can be used for other volumes that we don't have a formula for. Plus, we'll be able to check our work and make sure our method is correct by first trying it on the volume of a sphere. Alright, we'll start with a simpler volume. That's the volume of a cylinder. The volume of a cylinder is equal to the cross-sectional area, A, multiplied by the height, H. In this case, since the cross-sectional area is a circular area, the volume of a circular cylinder is pi r squared multiplied by the height. Now the idea will be to use this simpler volume, a cylinder, to calculate the volume of something that's more complicated, like a sphere. This is analogous to calculating the area under a curve. We used a simple shape that is a rectangle to help us calculate the area under the curve. Alright, I'm going to start by drawing a cross-section of a sphere, which is a circle, and then start filling it in with some cylinders. They look like disks, and this method is going to be called the disk method. And notice it looks like a rough approximation of a sphere. And we know how to calculate the volume of this shape because it's composed of cylinders. The volume of a cylinder is the cross-sectional area times the height. So we'll call the height delta x, and we get this summation, right? There's 7 cylinders, so we gotta add up 7 things. The things that we're adding is the cross-sectional area times the height, which we're calling delta x. The reason why we're calling it delta x instead of h is because we can think of the top half of that circle as square root of 1 minus x squared, so we can think of it as a function. And notice the radius of each one of my cylinders, or each one of my disks, is determined by this function, right? It's determined by the square root of 1 minus x squared. So it's very analogous to when we find the area under the curves, where the height of the rectangles were determined by the function values. The radius of these disks are determined by the function value depending on where your x is, and I happen to use midpoints. So the middle of my thickness of the cylinder is where the function intersects each cylinder. Now I can plug in what my area is. Well, the area of a circle is pi times r squared. Now I know that the radius is determined by my function value, square root of 1 minus x squared. Now let's look at when we use more cylinders. There's a picture of when we use 20 cylinders, and it looks more like a sphere now. And here's a picture when we use 50 cylinders, and now it looks really close to a sphere. And we have that same formula above, but now we're just summing 50 cylinders instead of just 7 or 20. Alright, now you should be thinking, well, we should just let n go to infinity, right? Use an infinite number of cylinders. And that would be the integral from -1 to 1 of pi times r squared, where r is determined by the function square root of 1 minus x squared. And that would give us the exact volume of the sphere. So let's check it out. That integral, well, we could simplify a little bit because the square root and squared part kind of cancel each other out. And I can pull that pi out front since it's a constant. And then take the antiderivative and evaluate at 1 and -1 and subtract the 2, and I'd get 4/3 pi. And you should double check with the volume of a sphere formula, right? The volume of a sphere of radius r is 4/3 pi r cubed. This is radius 1, so it checks out. Alright, there we are. That's our method where we calculate the volume of an object using simpler volumes like cylinders or disks. And it's very analogous to when we're finding areas under a curve using rectangles. We're just finding volumes using cylinders. Well, that's it for this video. Hopefully you feel warmed up for class.